All right, let's do another example of a continuous random variable. So this is example 2. This time we are starting with the PDF. And let's go ahead and just draw this to get a sense of what this distribution might look like. It is a little different from the previous one. Now our support is from 0 to 1, and our function is 3x squared. So to draw these things, I often just draw a couple of points so to sort of extrapolate the function. And this doesn't have to be perfect, it's just trying to get a sense of what the problem looks like. So let's go from 0, 0.25, 0.5, 0.75, and 1. At 3, 0 squared, that's just going to be 0. 1/4 squared is 1 over 16, so that just becomes 3 over 16. 1/2 squared is 1 over 4, so that's 3 over 4. 3/4 squared is 9 over 16. Times 3 is 27 over 16. Check my math. 27 over 16. Okay, then 1 squared times 3 is 3. All right, so this is a interesting function. We'll go ahead and plot. So 0 is at 0. 1 is at 3. 0.25 is at 3 over 16, which is kind of on the smaller end over here. Half is almost at 1, it's at 3/4. And then we have a bigger one that's not quite 2, but closer to it. So we could sort of extrapolate what this function looks like. And this is our PDF. It has non-negative values between 0 and 1, and after 1 it is 0, and before 0 it is 0. So we have our PDF there. Now we want to start with calculating the expected value of x. Expected value of x, we have that over here. It is defined over here, so we'll go ahead and use that definition for this problem. Now, this definition has from -infinity to infinity, but this particular PDF has only non-negative values between 0 and 1, or sorry, only positive values between 0 and 1. So a lot of times people just go ahead and jump to only considering the values of the support, and that's fine. But if we want to be a little bit more complete, it looks like this. For negative infinity to 0, x times, and then f of x evaluated in this region is 0, dx plus 0 to 1, x times 3x squared, that's our PDF, dx plus 1 to infinity, x, and this would be 0, because again, we are past 1, dx. And we know the integral from 0 from any range is still 0, and this is still 0. This step that I just did isn't entirely necessary. Again, most people will just look at the support and sort of skip this step and just write the following. And that would be fine. I just wanted to show it to connect the definition I gave you to a real problem that doesn't necessarily need the full real numbers. Okay, so now we're ready to evaluate. This just becomes 3 over 4 times x to the 4th from 0 to 1. So we get 3 over 4. 1 to the 4th power is 1 minus 0 to the 4th power. I don't need to write the 4th. And we have the expected value of x is 3 over 4. All right, now we want to find b, which is the CDF. Now, I also know that, I've already gone CDF to PDF, but I know that I can go PDF to CDF as well using this property. So I'll put this property over here as a reference. This is the property I'm using from the notes. I'll put it in blue. Now I'm going to write this as f, and I'm going to put x naught. So I'm evaluating up to x naught. So my integral's got to go from, and just as a reminder, I know I've already said this in these videos, but this would be x. What's the probability of x up to x naught? So I'm going to go from negative infinity to x naught. And then I need my CDF function, which is 3x squared. And this would be dx. Now, this is a useful note-keeping thing. I put x naught here, so I don't get confused with bookkeeping later or my notation later if I define this as just x and I took my integral from x. That could be a little bit confusing. That's why this definition that I gave you up here has t over there. So whether you use a t or you use x naught and then an x, something like that is useful. If you are very good at keeping track of everything, you might be able to get away without that, but I think this makes it a little easier. All right. Also, again, our function is not defined through negative infinity. So I actually don't need to write negative infinity here. I can, for completion again, do something like this. And then it's at 0 dx plus 0 to 1, or sorry, x naught, 3x squared dx. Again, this step is not entirely necessary, but if it's useful for you, you are welcome to do it. You're also just welcome to skip it. So evaluating that second term over here, I have 3x, and this would be 3x to the third over 3, evaluated from 0 to x naught. And then we get x naught to the third minus 0 to the third. And then we get x naught to the third. But again, we are not done yet. CDFs and PDFs have particular ranges in which they're defined. So we got to make sure we put that there too, the support. So in this case, this is if x naught is in between 1 and 0. And it is 0 if x naught is less than 0. But there's also an additional situation that we have to think about, which is when x naught is greater than 1. If x naught is greater than 1, then this function is 1. X naught is larger than 1. So let's go ahead and plot this to get a visual. And that is the next part of this problem. Our CDFs, the maximum possible value is 1, the minimum is 0. Our function in particular is defined between 0 and 1, or at least that's where it's interesting and changing. And then we have these other points here. When I draw things just to get a sense of what they look like, again, I just draw a few points to get a visual, and I sort of extrapolate after that. So let's do 0, 1/4, 1/2, 3/4, and 1. At 0, 0 to the power of 3 is still 0. 1/4 to the power of 3 is 1 over 64. 1/2 to the power of 3 is 1 over 8. 3/4 to the power of 3 is 24 over 64, which is approximately 0.42. And then 1 to the power of 3 is still 1. So drawing this out, 0 and 0, 1/4 and 1/64, it's still really close to 0. 1/2 and 1/8, and this way, my current scale, it's still pretty low. 3/4, it's about 0.42, that's almost at the halfway point. And at 1, we're near 1. So if I were to draw this function, it looks something like something like this as an approximation. And over here are the points that are a little bit more interesting and changing. And then this is where it becomes 1, and this is where it becomes 0.